Okay, so here's the second video for class 4. In the previous video, we introduced pressure vessels and these equations for the thick-walled pressure vessels. Now, more often than not, if you have had pressure vessels in mechanics and materials, you've had the thin-walled approximation. It's very common to do. You got to make sure that you only use it when it's appropriate. And there's a very easy derivation for this. Before I go any further, let me make sure that we highlight the limitations of the pressure vessel, these thin-walled approximations. And let's take a look at where this stuff is in the book too, because it's very good to keep track of where things are in the book. So you'll see that section 314. You'll see a lot of these are general equations for inside and external pressure vessels, but we only are dealing with internal pressure vessels. So these are the equations that we introduced right here. Here's tangential, and which is also called hoop, remember. And then we have radial, and then if we get to the next page, at least it was in this edition, you'll see here's the longitudinal, and here's the figure that we dealt with. And right here's where thin-walled begins, and right here is an important statement that we want to make, right? When the wall thickness of a cylindrical pressure vessel is about 1/10 or less of its radius, the radial stress that results from pressurization is quite small compared to the tangential stress. And as a consequence, we can really kind of ignore the variation between the inside and the outside. So this distribution right here doesn't really matter all that much when the wall gets really thin, and we can pretend as if it is pretty close to being one single value, right? So here's stuff that I have written down, and here's the equations that we would want to look at, right? So for the longitudinal, it gets real easy. It's just the pressure times the inside diameter divided by 4 divided by the wall thickness. Okay, so that's equation 354. Now, I have accidentally, and in some books, I recall seeing, they just put the diameter there. Some books might just say diameter, and you have to decide whether it's the inside diameter, the outside diameter. Some books might even use the average of the inside and outside diameter. Remember though, this is an approximation. So it might be good for us to work through them while we're learning as students and checking to see what's the difference that would make in the answer. Like how many percentage difference would that make, whether you use the inside or outside diameter. But they're supposed to be pretty close to each other. Now Shigley does this right here. You see equation 352. You'll see that they have the pressure, inside pressure. Now, I don't know why they decided to make it inside. They're all inside pressure, but okay. Times DI, right? So that's the inside diameter divided by 2T. Notice that would tell us that this is the average hoop stress. The average hoop stress is 2 times the longitudinal stress. So once again, it's pretty much twice the amount of the thing. They also give us, for whatever reason, they say as an approximation, you could also find, we want to be a little bit more closer to the correct answer, I guess, for a thin-walled approximation. It's already called an approximation. That you would take the inside diameter and you would add the thickness to it, and then multiply that by the pressure and divide by 2T. So you could compare these two things. But that maximum stress is on the inside surface, right? That's on the inside surface of the thing. So if we're going to look for stresses on the outside surface of this thin-walled approximation, we're going to use this equation right here. The only time you should add T to this DI right here is if we're looking on the inside surface, right? So I like to go ahead and go through a brief derivation of this. It's a really easy derivation to do. I actually kind of have it memorized, or almost have it memorized, right? So But it's good to keep this kind of thing in mind, right? So, like, if we have this pressure vessel, this is a big, just a big generic pressure vessel right here, and we wanted to try to find the stresses in it. First, let's take a cross section of this thing, and of course, it's got end caps on it, right? So, the pressure is pushing in that direction, trying to make this thing longer. It's the longitudinal stress is what that action is going to cause. Right? So if you're taking a cross-section look inside this piece right here, you could find, if you made an approximation, the area of the steel, right, that was on there, right? That area of the steel is going to be approximately the circumference times the thickness. Does that make sense, right? You can think of like a ring right here. We're seeing a ring like this right here. So there's the cross-section of this. If you have the circumference of the thing and you multiply it by the thickness, if it's thin enough, then the area, this area that you would have right there would be the circumference times the thickness, right? And if you were going to get what the total force was going to be that's inside this metal, right, what you would do is you would have the stress, this longitudinal stress, you'd have that multiplied by the area of the wall, right? Let's call that the area of the wall. And remember, I said it was going to be like pi d times t, circumference times thickness, to give that. It's an approximation, right? Well, you would say if you were going to do an FBD of this, and if that's the positive x direction, right, the longitudinal is aligned with the x direction according to this. In the negative direction, it would be the pressure, they called it capital P, the force of the total force due to this pressure on the end cap would be that pressure times pi r squared. Right? So it would be, we would set that equal to what they're saying is capital P, which is going to be pressure times the area that I'll say is X. And so that's going to be this area right there, which is going to be pressure times, and I'm going to deviate, I'm going to pi over 4 d squared, right? And maybe that's di squared, I guess. It makes sense. So it's even though they're showing it as the radius squared, I'm going to go ahead with diameter here instead. Well, let's take a look, because I have diameter up there. Let's put this longitudinal times this area, pi di. All right, so I'm going to use the inside diameter of this, even though that's still an approximation, times T is going to be equal to pressure pi over 4 di squared. Well, look at this. The pi's cancel out. One of the diameters cancels out right there. And what we're left with is the longitudinal is going to be equal to pressure times diameter divided by 4t. Isn't that the equation that we just used a second ago? That when we introduced this thing and said, here are the thin-walled approximation equations, right? So let's go back to this, and we said right there. We just derived it just from that simple free body diagram. So that's the approximation. That's where that equation is coming from. Now, I'd find my mouse. There you go. It came back. Let's do the same thing for the hoop stress. All right, so now hoop stress, you can see that it's written right there. Hoop stress is going to be acting, we're going to take a segment we'll call delta x, right? So there's only going to be a short little segment of this piece right here. And we're going to slice it down the center as well, right? So we have hoop stress acting right here and right here. So it is acting on an area of the wall that looks like that and like that, right? And that area of the wall, and you could, if we're going to do stresses first, we would say that's going to be the tangential, aka hoop, right? And it's in two places, so it's times 2, and it's going to be acting against this rectangle right here, right? And that rectangle is delta x times t. So we have delta x t. times the thickness, right? It's just a rectangle here and a rectangle here, and here's the stresses in both of them. Well, that thing is fighting against the internal pressure of the thing, right? The internal pressure times this area right here, which is going to be, well, they're showing it as 2R, but that's just this DI, right? So it's this pressure is acting at DI, that's this length right there, times delta X, this distance. Well, check this out. Look at that. Delta X cancels out. We get tangential here is going to be P DI divided by 2T. You'll recall from our equations over here, that's this guy right here. That's that average tangential stress. Now, it does vary a little bit from the inside to the outside, but our thin wall approximation is basically saying it's so thin that that distribution doesn't matter, and we're just going to take what the average of that tangential stress is going to be. And this figure kind of summarizes what those stresses look like on an inside surface and an outside surface. So let me just summarize again what our equations are going to be, right? So for a thin-walled thing right here, this is only good when we have to let's go back to Shigley. Let's take a look at what it says again. That the thin-walled is only good when it's 1/10 or less of the radius, right? So we can make a ratio. So we need to make a ratio each time and say when T over R, and you say which one? Well, use either the inside or the outside radius. I don't care. When that is less than 0.1, then we can use these equations. And we have hoop, which is going to be this. And maybe I'll go ahead and write the average right in there. Average is P DI over 2T. But make sure, we might, and I should also point out, okay, in Shigley. Let me point out where this is in Shigley and why this can mess you up. It's because right here is where it says the average hoop is equal to this right there, Pi DI over 2T. You see that? They're also showing you how you can integrate that and to get to the same thing. But notice this is the equation you want to use. Unfortunately, it's because it has this stuff in the middle, students tend to just jump to this one right here. This is the max, which remember is only on the inside surface right there. So because these, you usually give open book tests, you don't have equation sheets, people often will just default to hunting through and jumping to the first equation that they see. And this one is easier to see than this. But this is only on inside surface. And they're just being nitpicky because it's already an approximation. This is already an approximation. And so I tend to say don't use this one unless you just, want for some reason to do it on the inside surface of the thing, make it clear. All right, so the longitudinal, so I just wrote it as a cursive. Longo right there, L is P DI 4T. It's 1/2 of the hoop. And then remember, radial is going to be equal to negative P, right? And only on inside surface. And then to answer this, when can the thin wall be used? When, I'll just repeat, T over R is less than 0.1. So there you go, and I am going to end the video here and then do an example in the next video because I think short videos are better. Thank you so much, and we'll talk again in a moment. Pressure vessels. Pressure.